Wow, there's almost no signal here.
So, what is the optimal sub-exposure time now?
What?
If the image has almost no signal, what is the optimal sub-exposure time?
Well, we could put it in my Sublength calculator to...
That's not going to work right now. This image is an RGB image, so the histogram will have 3 peaks, and the calculator won't be able to use sky glow to measure the swamp factor. There is basically no sky glow.
So, we can't figure it out then?
Well, there might be a way to fix things. It won't be perfect, but it should be decent. Let's go over it. Welcome to Deep Sky Detail.
In my last video, I introduced a sublength calculator. It tries to figure out what the optimal subframe length should be for your astrophotography images. Details of the theory and how to use it are in that video, but a quick recap is that with it, you could use a dark or a bias frame along with a light frame to figure out what your minimum sub-exposure times should be to swamp the read noise of your camera and get optimal signal-to-noise ratio. The histograms of the bias and light frame provide the app with the relevant information. And based on those, it compares the sky glow in your light frame's image to do that. The reasoning being that if the sky glow part of the histogram is above the read noise histogram, then the deep sky object signal is also above the read noise. To download the calculator, which can be used in Windows as an executable file or as a SiriL script, you can go to my Buy Me a Coffee page or to GitHub. The link will be in the description. There is also an online version that is a little bit more limited in terms of how big the files can be that you can upload, but that is also an option. Again, link is in the description. And the calculator has 2 flaws, most affecting one-shot color cameras. The first is the Bayer matrix. Not all of your pixels are going to be part of the same histogram. Most likely, the green pixels in your image are going to be brighter than the red and blue pixels are going to be. That's going to mess up the variance estimates that the tool uses, giving too short of a minimum sublength for one of the estimates. To fix that, the tool can now analyze each channel individually. It gets the Bayer pattern using the FITS file information. If it can't find, assumes that the Bayer patterns are RGB. So let me load in a broadband color image and its corresponding bias frame and put in the relevant information. Note to make sure that you're putting in electrons per ADU into this gain parameter here, not the raw gain. So a ZWI ASI 2600 MC Pro at 100 gain corresponds to 0.24 electrons per ADU. Okay, so if we look at this new drop-down menu called Color Filter Gray Channel or CFA channel, it by default says luminance. This combines all of the RGB pixels, which we probably don't want. If we look at the light frame histogram in yellow, it is really spread out. And that's because it's 3 histograms that each have their own means and standard deviations. So instead of looking at all of the pixels, let's just change this drop-down menu to green. The histogram of just the green channels is shown, which doesn't look spread out anymore. It gives us more accurate minimum subframe numbers for the green pixels. You could do this for the red and blue channels too. If you're focused on reflection nebulae, which are often blue, then maybe you want the blue pixels to not be read noise limited. So the blue channel might be the most important for those types of targets. If you're imaging galaxies, then green might be the most important channel for you. And if you're imaging emission nebulae, then red might be the most important because those pixels should pick up on the hydrogen alpha wavelengths the most. But if in doubt, I'd say go with green. The second problem also has to do with a Bayer matrix. So if you are in fairly dark skies, probably anything less than Bortle 5, and you're using a dual narrowband filter that blocks about 98% of the sky glow, and behind that you have a Bayer matrix, which for any given pixel is probably filtering out 2/3 of the remaining sky glow, then even a 180-second image may not have much measurable sky glow signal at all. The calculator needs the sky glow to figure out the minimum sublength, or at least it used to. The logic being that if the sky glow is above the read noise, then the DSO signal is also above the read noise. But if there's no sky glow, the DSO signal may indeed be above the read noise, which is what we're really interested in anyway. But many of the pixels in these low sky glow, low signal subframes are only measuring read noise. And so the sublength estimates then become way too long, and it's overkill for the parts of the image that actually do have signal. So there is now another drop-down menu. It's called Narrowband Correction. So if you find that the subframe length is way too long, you're probably in dark skies using a narrowband filter. When you select yes for the narrowband correction, instead of estimating the sky glow signal, the calculator will try to now estimate the DSO signal. And if your subs are still too long, maybe you're in very dark skies with a filter, or you're imaging a target with very little signal from a particular emission line like O3 in the California nebula, then you may want to decrease the swamp factor to something like 3. Your camera will still roughly be 85% efficient compared to a perfect camera with no read noise. I just like to stop and thank everyone who has supported the channel on Buy Me a Coffee or as a channel member. I really appreciate it. And if you'd like to see some real-world experiments with sub-exposure length, consider this playlist here. Thanks for watching.